Welcome to today's problem walkthrough. In this session, we'll explore problem number 260, single number 3. We'll dive into the problem statement, examine some intuitive approaches, and work our way towards the optimal solution. Let's get started. In this problem, you're given an integer array called nums. Within this array, there are exactly two elements that appear only once, while every other element appears exactly twice. The task is to find these two unique elements and return them as a list. The order of the two numbers in the output doesn't matter, so x, y, and y, x are both acceptable answers. For the input format, the array will always have 2n plus 2 elements, which ensures that there are two unique numbers and the rest appear in pairs. The output format is simply a list containing the two unique numbers. Let's consider an example to better understand this problem. In the first example, the input array is nums equals 1, 2, 1, 3, 2, 5. Here, the numbers 1 and 2 each occur twice, while 3 and 5 appear only once. Therefore, the output is 3, 5. Since the order of the two unique numbers doesn't matter, 5, 3 is also a valid answer. Now, let's look at another example. For the input nums equals -1, 0, 0, -1, 2, 3, the numbers -1 and 0 each appear twice, while 2 and 3 appear only once. Thus, the output is 2, 3, or 3, 2, as the order is not fixed. In the simplest case, consider the input nums equals 0, 1. Here, the array contains only two elements, both of which are unique. Since there are no duplicates, the output is straightforward 0, 1, or 1, 0. This demonstrates how the problem handles the smallest possible input size. Now, let's review the constraints and additional notes on what to consider when solving this problem. The constraints specify that the length of the array nums is at least 2 and at most 30,000, and it will always be even. The array contains integers, and exactly two elements appear only once, with all other elements appearing exactly twice. Regarding edge cases, for the minimum input size of 2, such as a, b, the output will simply include both unique numbers. The solution must also handle negative integers properly. Since the input array can be unsorted, the solution should work regardless of the order of elements. Finally, the output order of the two unique numbers isn't fixed, so either x, y, or y, x is acceptable. These considerations ensure the algorithm is robust and handles all valid scenarios correctly. When solving this problem, we considered a few approaches, starting with the brute force method. The idea here is straightforward. For each element in the array, we compare it against all other elements to count its occurrences. Once we have the counts, we identify the two unique numbers, those that appear only once. While this method is simple in concept, its implementation involves nested loops, leading to a time complexity of n squared. This makes it inefficient for large datasets. Additionally, it has a space complexity of 1, since we're not using extra memory, but the poor scalability is a significant drawback. Another approach we explored is using a hash map to count frequencies. Here, we traverse the array once, storing each number's count in the hash map. Afterward, we extract the keys with a value of 1 to find the unique numbers. This approach improves time complexity to n, but it comes at the cost of requiring n extra space for the hash map. While more efficient than brute force, the memory overhead can become problematic for very large arrays. Both of these methods have their own trade-offs, but neither is ideal for this problem. To address these limitations, we turn to an optimized approach using bit manipulation, which leverages the properties of the XOR operation. The intuition here is that XORing all the numbers in the array will cancel out the duplicates, leaving us with the XOR of the two unique numbers. From there, we use a bit mask to isolate these two numbers based on their differing bits. Let's break this down step by step. First, we compute the XOR of all the numbers in the array, which we call XOR_all. This value represents the combined XOR of the two unique numbers. Next, we identify the rightmost set bit in XOR_all using the formula bitmask equals XOR_all and XOR_all. This step is crucial because the set bit indicates a difference between the two unique numbers. Using this bit mask, we partition the numbers in the array into two groups, one where the bit is set and one where it is not. Finally, we XOR all the numbers within each group to isolate the two unique numbers. This approach is highly efficient, with a time complexity of O(n) for a single traversal and a space complexity of O(1), since no additional data structures are needed. The use of XOR properties simplifies the solution and makes it both elegant and powerful. Ultimately, we chose the bit manipulation approach because it strikes the perfect balance between efficiency and simplicity. Unlike the brute force method, which is computationally expensive with a time complexity of O(n squared), or the hash map approach, which requires O(n) extra space, bit manipulation achieves optimal performance in both time and space. The key insight here is recognizing that XOR operations, combined with a bit mask, allow us to isolate the two unique numbers in a single pass through the array. This eliminates the need for additional memory, making it especially suitable for handling large input sizes. While the brute force method is easy to implement and the hash map method is faster, bit manipulation stands out as the most elegant and efficient solution. By leveraging these XOR properties, we reduce the problem to its simplest form, offering a clear advantage over other approaches. To solve the problem, we need to identify two unique numbers in an array where every other number appears exactly twice. The key challenge is to do this efficiently in both time and space complexity. The optimal approach leverages the properties of the XOR operation. Let's recall these key properties. XORing a number with itself results in 0, XORing a number with 0 leaves the number unchanged, and XOR is both commutative and associative. These properties allow us to cancel out duplicate numbers while isolating the two unique numbers. Using this, we can outline a step-by-step plan to solve the problem efficiently. The first step is to XOR all the numbers in the array together. This cumulative XOR operation, which we'll call XOR_result, effectively cancels out all the duplicate numbers because x(x) equals 0. What's left is the XOR of the two unique numbers, number 1 number 2. Since these two numbers are distinct, their XOR will always be non-zero. Next, we need to find a way to differentiate between number 1 and number 2. To do this, we identify the rightmost set bit in XOR_result using the expression XOR_result and XOR_result. This set bit represents a position in the binary representation where the two numbers differ. This distinction is crucial because it allows us to partition the numbers into two groups based on whether this specific bit is 1 or 0. Once we have the rightmost set bit, we use it as a mask to partition the array into two groups. Group A contains numbers where the identified bit is 1, and Group B contains numbers where the bit is 0. This guarantees that the two unique numbers, number 1 and number 2, are separated into different groups, while all other duplicate numbers remain within the same group. Now, we XOR all the numbers in Group A, which isolates one of the unique numbers, number 1, since duplicates cancel out. Similarly, XORing all the numbers in Group B isolates the other unique number, number 2. Finally, we return these two numbers as the result. The beauty of this approach lies in how XOR efficiently isolates the unique numbers without requiring extra memory to track counts. This algorithm is highly efficient because it doesn't require any additional data structures, relying only on integer variables to store intermediate results. In terms of time complexity, the array is traversed 3 times, once to calculate the cumulative XOR, once to partition the numbers, and finally to XOR within each group. This results in an O(n) time complexity. The space complexity is O(1), as no additional memory is allocated beyond the variables used. Regarding edge cases, the algorithm assumes the input always contains exactly two unique numbers, so an empty array is invalid. If the array contains only 2 elements, the algorithm directly returns them as they are already unique. It also handles negative numbers seamlessly since XOR operates on their binary representation, and it's unaffected by the order of the input. Let's walk through an example with the input array 4, 2, 4, 6. First, we XOR all the elements together, for 2 to the power of 4 6. The duplicate 4's cancel out, leaving 2 6, which equals 4. This is our XOR_result. Next, we identify the rightmost set bit in XOR_result using XOR_result and XOR_result, which gives 4, binary, 0 1 0 0. This indicates that the two unique numbers differ at bit position 3. Using this bit as a mask, we partition the numbers into two groups. Group A, where bit 3 is set, contains 4, 4, and Group B, where bit 3 is not set, contains 2, 6. XORing Group A gives 4 caret 4 equals 0, and XORing Group B gives 2 caret 6 equals 4. The two unique numbers are 2 and 6, which we return as the result. This implementation solves LeetCode problem number 260 single number 3 using an optimal XOR-based approach. Here's the detailed explanation. Step 1 asterisk first, we XOR all numbers in the input array nums. The XOR operation ensures that all numbers appearing twice cancel out, leaving the XOR of the two unique numbers. Let's call this result XOR_result. Step 2 asterisk next, we identify the rightmost bit where the two unique numbers differ. This is achieved by computing XOR_result and XOR_result, where XOR_result is the 2's complement of XOR_result. This operation isolates the lowest set bit in XOR_result. Step 3 asterisk, we then divide the numbers into two groups based on whether a number has this bit set, number and diff_bit equals 0, or not, number and diff_bit equals 0. By XORing all numbers within each group, we isolate the two unique numbers because the duplicates cancel out within their respective groups. Step 4 asterisk, finally, the two results number 1 and number 2 are the unique numbers that appear only once in the array. We return them as a list. This approach runs in O(n) time and uses O(1) extra space, making it highly efficient for this problem. The critical insight lies in leveraging XOR properties and efficiently partitioning the numbers based on a single differing bit. This is the Java implementation for LeetCode problem number 260, single number 3. The logic mirrors the Python solution, using XOR operations to identify the two unique numbers in the input array. Key differences include the use of Java's type declarations and array structures. The code is concise and follows Java conventions for clarity and performance. To solve this problem, we start by finding the XOR of all the numbers in the input array. The XOR operation helps us identify the combined result of the two unique numbers, as all the duplicate numbers will cancel each other out. We initialize XOR_result to 0, then iterate through the array. For each number, we compute XOR_result caret equals number and update its value. For example, starting with 0, XOR with 1 gives 1, XOR with 2 gives 3, and so on. By the end of the iteration, XOR_result equals 6, which is represented as 110 in binary. This value is the XOR of the two unique numbers. Next, we need to determine where these two numbers differ. We do this by finding the rightmost set bit in XOR_result. This is calculated as diff_bit equals XOR_result and XOR_result. For XOR_result equals 6, the rightmost set bit is 2 in decimal or 010 in binary. This bit indicates a position where the two unique numbers differ, allowing us to separate them in subsequent steps. Now that we have the diff_bit, we can use it to divide the numbers in the array into two groups. These groups are determined by whether a number has the diff_bit set or not. We initialize number 1 and number 2 to 0. As we iterate through the array, we use the condition number and diff_bit to decide which group a number belongs to. If the condition is true, we XOR the number into number 1. Otherwise, we XOR it into number 2. For example, in the input array, the number 1 does not have the diff_bit set, so it is XOR'd into number 2. The number 2 has the diff_bit set, so it is XOR'd into number 1. Continuing this process for all numbers, we eventually find that number 1 equals 3 and number 2 equals 5. These are the two unique numbers in the array, and we return them as the result. In this example, the input array is 4, 6, 4, 7. We follow the same process as before. First, we compute the XOR of all the numbers to find XOR_result. Starting with 0, XOR with 4 gives 4, XOR with 6 gives 2, XOR with 4 gives 6, and finally XOR with 7 gives 1. So the final XOR_result is 1, which is 001 in binary. This value represents the XOR of the two unique numbers. Next, we identify the rightmost set bit of XOR_result using the formula diff_bit equals XOR_result and XOR_result. For XOR_result equals 1, the diff_bit is also 1, corresponding to the least significant bit. This tells us that the two unique numbers differ in this position, which will help us separate them into groups. Using the diff_bit of 1, we now divide the numbers into two groups based on whether the least significant bit is set or not. We initialize number 1 and number 2 to 0 and iterate through the array. If a number has the diff_bit set, it is XOR'd into number 1. Otherwise, it is XOR'd into number 2. For instance, the number 4 does not have the diff_bit set, so it is XOR'd into number 2. The number 6 also does not have the diff_bit set, so it is XOR'd into number 2, resulting in an intermediate value of 2. The number 7 has the diff_bit set, so it is XOR'd into number 1, resulting in number 1 equals 7. After processing all numbers, we find that number 1 equals 7 and number 2 equals 6. These are the two unique numbers in the array, and they are returned as the result. In this example, the input array is 0, 1, 2, 1. The process begins with the XOR operation to find XOR_result. Starting with 0, XOR with 0 remains 0, XOR with 1 gives 1, XOR with 2 gives 3, and XOR with 1 again gives 2. The final XOR_result is 2, which is 0, 10 in binary. This value represents the XOR of the two unique numbers. To locate where these numbers differ, we compute the rightmost set bit of XOR_result as diff_bit equals XOR_result and XOR_result. For XOR_result equals 2, the diff_bit is also 2, which is 0, 10 in binary. This tells us that the two unique numbers differ at the second bit, enabling us to separate them into groups based on this distinction. With the diff_bit determined as 2, we separate the numbers into two groups. Using the condition number and diff_bit, we XOR numbers into number 1 or number 2 accordingly. Starting with number 1 equals 0 and number 2 equals 0, the number 0 does not have the diff_bit set, so it is XOR'd into number 2. The number 1 also does not have the diff_bit set, so it is XOR'd into number 2, resulting in number 2 equals 1. The number 2 has the diff_bit set, so it is XOR'd into number 1, resulting in number 1 equals 2. Finally, the number 1 does not have the diff_bit set, so it is XOR'd into number 2, resetting number 2 to 0. After processing all numbers, we find that number 1 equals 2 and number 2 equals 0. These are the two unique numbers in the array, and they are returned as the result. Here, we break down the time complexity of the solution step by step. First, in step 1, we iterate through the entire input list nums using a for loop. During this iteration, we perform an XOR operation for each number, which is a constant time operation. If the list has n elements, this step takes n time. In step 2, we use the operation XOR_result and XOR_result to isolate the rightmost set bit. This is a bitwise operation that executes in constant time, 1, regardless of the input size. Step 3 involves dividing the numbers into two groups based on the isolated set bit and performing another XOR operation for each number. Similar to step 1, this requires a single pass through the list, resulting in an additional n time complexity. Finally, step 4 simply returns the two unique numbers, which is a constant time operation, 1. Together, these steps demonstrate how the solution processes the input efficiently at each stage. Now, when we combine the time complexities of all the steps, we get n for step 1, 1 for step 2, n for step 3, and 1 for step 4. Adding these together results in an overall time complexity of n. This is the best possible time complexity for this problem, as we must process all n elements in the input at least once to find the two unique numbers. On the other hand, the space complexity is straightforward. The algorithm uses only a few integer variables, such as XOR_result, diff_bit, number 1, and number 2, to store intermediate results. These variables occupy constant space, 1. Since the input list is not modified and no additional data structures are used, the total space complexity remains 1. This makes the solution not only time efficient but also space efficient. When analyzing the best, average, and worst cases for this algorithm, we find that the time complexity remains n in all cases. This is because the algorithm always processes the input list nums in a single pass during both step 1 and step 3, regardless of the distribution of numbers. Similarly, the space complexity is always O1, as the algorithm does not require any additional memory that depends on the input size. Comparing this solution to a brute force approach, we see significant space savings. A naive method might use a hash table or dictionary to count the frequency of each number. While this approach also has a time complexity of O(n), it requires O(n) space to store the hash table. In contrast, the XOR-based solution achieves the same time complexity while reducing the space complexity to O(1), making it a more efficient choice. To solidify our understanding, let's look at a mathematical proof for the big O complexity of this solution. The dominant term in the time complexity is the linear traversal of the input list during steps 1 and 3, which contributes O(n). All other operations, such as the bitwise calculations in step 2 and returning the results in step 4, are constant time operations, O(1). When we combine these, the total time complexity simplifies to O(n). As for space complexity, the algorithm's use of a fixed number of variables means that its memory usage does not grow with the size of the input. This makes the space complexity constant, O(1). These complexities highlight the efficiency of the XOR-based approach both in terms of time and memory usage. When solving the single number 3 problem, there are some common mistakes you should be cautious about. First, using a brute force approach with nested loops might seem straightforward, but it leads to a time complexity of O(n squared). For large inputs, this is highly inefficient and can result in time limit exceeded errors, making it unsuitable for competitive programming. While the logic might be correct, it simply doesn't scale well. Next, failing to account for edge cases can trip you up. For instance, arrays with only 2 elements, no duplicates, or an odd size can cause index out-of-bounds errors or produce incorrect results if not handled carefully. Another issue is ignoring input constraints like integer bounds or array size limits. Overlooking these can lead to undefined behavior or, worse, runtime errors. Lastly, improper use of hash maps, such as forgetting to check if a key exists before accessing it or mishandling the increment operation, can lead to inaccurate results or runtime crashes. Avoiding these pitfalls is crucial for writing a robust solution. Another common mistake is misunderstanding XOR properties. XOR is a powerful bitwise operation, but its properties, like a XOR equals 0 and a XOR 0 equals a, must be applied correctly. Missteps here can completely derail your logic and lead to incorrect outputs. When preparing for interviews, there are several strategies to keep in mind. Start with a brute force approach to demonstrate your understanding of the problem, but make sure you quickly transition to optimized solutions involving hash maps or XOR to showcase your ability to improve efficiency. Always clarify constraints with the interviewer, such as the size of the input array or the type of elements, to avoid incorrect assumptions. It's important to recognize XOR patterns, as they can be a key insight for problems involving unique elements. Explicitly discuss how you handle edge cases, like empty arrays or large inputs, to demonstrate thoroughness. Finally, be ready to discuss trade-offs between different methods, such as the balance between time complexity and space usage, to show a well-rounded understanding of the problem. The concepts used in single number 3 are closely related to other problems that you may encounter. For example, LeetCode 136, single number, asks you to find the single non-duplicate element in an array where every other element appears twice. Similarly, LeetCode 260, which we're discussing, involves finding 2 unique elements in an array where every other element appears twice. LeetCode 137, single number 2, introduces a twist where every other element appears 3 times, and you need to find the single unique element. Another related problem is LeetCode 268, missing number, where you identify the missing number in a sequence ranging from 0 to n. Beyond these related problems, there are alternative approaches worth exploring. For instance, the hash map approach involves counting occurrences of each element and identifying those with a count of 1. This method is efficient in terms of time complexity at O(n), assuming a good hash function. However, it requires O(n) space due to the hash map, so it's best used when memory constraints are not a concern and the input size is manageable. You can also consider the sorting approach, where you sort the array and then compare adjacent elements to find the unique ones. While the time complexity here is O(n log n, due to sorting, the space complexity can be reduced to 1 if the sorting is done in place. This makes it a good option when memory usage is a higher priority than achieving the best possible time complexity. However, if you're looking for an approach that is both time and space efficient, the XOR method is often the best choice. By leveraging XOR properties, you can cancel out duplicates and isolate the unique elements with a time complexity of n and a space complexity of 1. This approach is ideal when both optimization and adherence to problem constraints are critical. Choosing the best method ultimately depends on the specific requirements and constraints of the problem you're solving. Great job reaching the end of this session. To recap, we covered how to solve problem number 260 with an optimal approach using bitwise operations. Remember the importance of XOR and how it simplifies problems involving pairs. Keep practicing, and don't forget to like and subscribe for more content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!